Okay, welcome to Related Rates. This little introduction isn't in the notes package that I handed out to you, so you're going to want to jot this down. People in the room here and the people who've been online with me for the last 6 or 7 minutes have already been copying it out. Those of you watching this video at home, feel free to just pause the video and jot it down. If you look in your OneNotes folder, this page is attached to the beginning of the notes package that I handed out a hard copy to you in class. So let's take a look and see what it says. So far in Unit C, we've used derivation, chain rule, and implicit differentiation to find slopes of curves. We always try to keep in mind that slope's definition is that it's a rate of change. The language, of course, that we use now is we say change in y divided by change in x, or derivative of y with respect to x, I guess is the way we kind of say it now. And now, where we're going to go from here is towards some word problems. We're going to look at applications of this idea of rate of change in physical situations where more than one measured value in a system is changing at some rate. And because these rates of change affect one another in a mathematically definable way, we call them related rate problems. These are sort of classic calculus problems. For our very first example, I want you to consider this, the page that I'm talking about. People have been jotting this down because I didn't hand this one out. Okay, so a pebble is dropped into a still pond and it creates an expanding ripple in the shape of a circle. So I think everybody's seen what I'm talking about here. I'll show you what I'm talking about here. That's something like this. Right, just a slow motion. Pick one circle and sort of follow it. There we go. There comes the circle. I'm following that circle. I'm following that circle. I'm following that circle. So everybody's seen something like that, right? So that's the idea. So a pebble dropped into a still pond creates an expanding ripple in the shape of a circle. We start measuring the radius of the circle when it's 3 centimeters, and we find that it's growing at a rate of 1 centimeter per second. So we want to know at what rate is the area of the circle growing. And for maybe a more simple animation of that, I have a little GeoGebra file here. So if we drop, let's get this thing going here. If we drop a pebble, I don't know why this isn't working. Oh, hang on. There we go. Drop the pebble. You can see the circle growing. Let's reset that. And notice on the right-hand side here, I have a nice little chart where I'm comparing, as time goes on the horizontal axis, how much the radius grows in red versus how much the area grows in blue. So we drop the pebble at 0, 0, and that circle grows. And of course, this red line here, notice that is, well, you could probably guess what that is, right? That's the slope of area's curve. So that would represent the rate of change of area. And of course, it's going to be, a tangent to the curve. And we would like to solve this problem. At what rate is the area of the circle growing? So let's see what we can do with this problem. What do we know for starters? Well, we know that there is a formula that relates radius to area. The area of a circle is pi r squared. We also have a couple of things that we know. We know that at some point we want to find a radius of 3, and we also want to find the change, or we don't want to find, we're given that the change in radius over time is 1. I guess I could put units on these, right? So this is centimeters, and this is centimeters per second. So there's all the information I know right now. How am I going to find dr by dt? Well, I'm going to find the derivative of a with respect to t. So the derivative of a with respect to t is pi, let me draw that a bit better, pi times, now here's the problem, this of course isn't a, so I have to kind of use chain rule on this, right? So I'm going to have to say that this is 2, oh hang on, I'm having some pen issues here. So this is 2 times r times the dr by dt. Right, and there's my chain rule. Okay, so this is what I'm looking for, right? I want the rate of change of the circle. So this is the variable I'm looking for, right? The change in area with respect to time, which is the rate that area is growing. And I have pi times 2, and I know r is 3. And I was given the rate at which radius is changing, so I can just replace that with a 1. And since this was centimeters and this was centimeters, and I'm dividing by time, or actually I should say this was centimeters and this was centimeters per second, I'm getting an answer in centimeters squared per second. And I'll just leave it in terms of pi. It's 1 times 3 times 2 times pi, so it's 6 pi centimeters squared per second. And there we go. There's our first related rate problem. The rate at which area is changing is related to the rate at which radius is changing because those two variables relate to each other in a specific formula mathematically. And we can find one or the other using our chain rule, as long as we're given one of them. Okay, any questions so far? All right. Now we can move on to the page that you have handed. You don't have to write so many notes anymore. And the notes kind of start with some suggestions on how to approach these problems. Determine an equation that relates two or more quantities together. In the case of the last example, we related area and radius. Differentiate both sides to solve for the variables or rates of change that we want. Number 3 is good luck. That's nice. Maybe if there's one other thing I might add to this. Of course, I like to organize my givens. Notice that I kind of started this problem by sort of making a little list of what it was that the information of the question gave me. Okay, I got a question over here. Why is it centimeters squared? Because radius is in centimeters, and this rate is in centimeters per second, right? So think of it as centimeters times centimeters per second, so that's centimeters squared per second, which makes sense because area is in, right, a squared unit. Does that make sense? Another question. That's, yeah, excellent. What if this question had been different and I'd have been told, for example, so the question is, what if I was trying to find this? Well, then I would need to know that. Right? I'd need to be told the change in area and then find the change in radius. Well, it depends. He's asking, couldn't we just ignore the initial value and just kind of assume that this 3 centimeter mark here is t equals 0, for example? Sometimes there are problems where that kind of approach works, but not always. And you'll see why as we get into more examples. Okay, let's take a look at example number 1 here. That was example 0. I added that one later because I wanted a super easy one for the first example. They get harder. So look at example 1. The length of a 12-foot by 8-foot rectangle is increasing at a rate of 3 feet per second, and the width is decreasing at 2 feet per second. So I'm going to start by kind of just sketching a rectangle and sort of defining my variables here. So I'll call the length here x and the width y. And okay, what do I know? Well, I know at some point in the growth, I guess maybe my starting point, if you like, that this thing is 12 feet by 8 feet. But I know that that's going to change. Why do I know that's going to change? Because I know that the change in x with respect to time is it's increasing at 3 feet per second. And I know that the change in this y is that it's decreasing at 2 feet per second. So I'm going to call that a negative because it's getting smaller. So now, can you kind of imagine what that rectangle is doing? It's, as time goes on, this line's getting longer, and this line's getting shorter. So they're changing. Now, how is that going to affect how fast is the perimeter changing? Maybe first of all, let me show you another little animation of that. Here's one that I just dug off of Desmos. It was ready-made for me, so I didn't have to make it myself. Where length and width are changing at different rates and in different directions. So in this case, it's the length is horizontal. And there we go. That's our situation right there. Not this part, but that part. It's getting, the horizontal is getting longer as the vertical gets shorter. So can you kind of picture that and imagine it now? And close that. By the way, the links for these are on the OneNote page too. Okay, so what else do I know? Oh, well, if I'm doing a perimeter, I guess I need to know how these two variables relate to each other in perimeter. And of course, perimeter is 2x's plus 2y's, right? Now, what do I want? I want the derivative of both sides of that equation. Okay, what am I actually looking for? I'm looking for this, right? How fast is the perimeter of the rectangle changing? That's this quantity right here, right? What's the change in perimeter over time? So I'm going to take the derivative of both sides, which gives me what I'm looking for on that side. But on the other side, because these aren't the variables of the derivative, they're related to them, but they aren't the actual variables of the derivative, I have to treat this like implicit differentiation, like chain rule. So it's going to be 2 times x to the 0, which is the x goes away, but dx by dt plus 2 dy by dt, right? And there's usually people at this point going, well, wait a minute, this we're used to. We see this in implicit differentiation all the time, but how come that's there? Well, again, think about it. X isn't actually the variable I'm doing the derivative of. It's perimeter. X is related to perimeter, it's part of perimeter, but it's not the actual variable you're finding the derivative of. So it's kind of like a double implicit differentiation. Okay? And I actually know this number and this number, right? This one's 3 and this one's -2. So I can now plug those in. And that's going to get me 6 minus 4, which is 2. And the unit we're in here is feet per second. Okay, any questions on how I did that? All right. How fast is the area changing? Okay. Now notice that the perimeter is increasing. It's increasing at a rate of 2 feet per second. Is the area going to be increasing? Think about the picture. The perimeter was definitely getting longer as it got skinnier, right? But was area getting bigger? Think about it. Let's go back to the picture for a sec. Oh, I closed it. Oh, hang on. I think I can just get to it over here. Yeah, here it is. I think I can actually play it in here. Well, maybe I can't. Oh, yeah, there we go. And let's see, how do I make this play? You know what, I better just go to the actual page here. There we go. Till I learn how to work with Desmos within my OneNote page, I better just go to the actual thing. Okay, so again, let's go this way, right? Or actually, I guess we want to head back to here. right? This is the way we want to go, this direction here. As I'm going this way, perimeter is definitely increasing, right? It's getting longer and longer and longer. You might be saying, yeah, but the widths are getting shorter. Yeah, but the lengths are getting longer faster than the widths are getting shorter. Does that make sense? So my perimeter is definitely increasing, and we just mathematically proved that. We got that it was increasing at a rate of 2 feet per second. But look at area. Remember that area is, of course, length times width. What's area actually approaching as I keep going? It's approaching 0. Eventually, it's going to get to nothing, right? Okay, so keep that in mind. What are we expecting area to do? Always nice to kind of have an idea as you're doing a word problem of what kind of answer you're expecting, so that if something goes off the rails, you goof up the formula, you goof up the calculus, you kind of can look at it and go, oh, that wasn't at all what I was expecting, and then you can kind of catch your own errors that way. So anyway, let's take a look at this. How fast is the area changing? So once again, I need a formula to relate all my variables to each other, and area is length times width, and I define length and width as x and y. And once again, I want how fast is the area changing. So what I'm looking for is the change in area over time. That's what I'd like to solve for. So I'm going to take the derivative of both sides of this equation. And that is product law, right? That's two different variables. And neither one of them are the variable I'm actually doing the derivative of. So it's going to be chain rule on both of them. So how about we'll do the derivative of x times the second variable plus x times the derivative of the first, or of the second variable. And I know all of these numbers, right? This is my x number, 20 feet. This is my y number, 5 feet. And I know the change from part A, right? The length was getting bigger at 3 feet per second, and at y being 5 feet. The width was getting smaller by 2 feet per second. Oh, actually, I should put the other number first, maybe. The x number here is 20. And the derivative of y, the actual width, is getting smaller at 2 feet per second. So notice I'm going to get 15 minus 40, which is negative 25. And this is feet squared per second. Okay, any questions on how I did that one? All right, now here's one that's really counterintuitive. Check out example 2. A young woman and her boyfriend plan to elope. You know what that means, right? Elope means that they're going to run away and get married. But she must rescue him from his mother, who has locked him in his room. The young woman has placed a 20-foot-long ladder against his house and is knocking on his window when his mother begins pulling the bottom of the ladder away from the house at a rate of 3 feet per second. This one's got some drama to it. How fast is the top of the ladder and the young couple falling when the bottom of the ladder is 12 feet from the bottom of the wall? Now this kind of might seem counterintuitive. It's one ladder, it's one object. How could one part of the object be moving at a different speed than another? Most people would probably look at this question, if they don't have a calculus background, and go, well, wait a minute. If the bottom of the ladder is moving at 3 feet per second, shouldn't the top of the ladder be moving at the same speed? It's one thing. It's a ladder. And that seems to be reasonable, but that's actually mathematically not how it works. And I can kind of show you that. Again, I've got a little animation here. Here we go. Falling ladder. So here's a ladder that's leaning against a vertical wall, and we're going to kick the bottom out. So kick out the ladder, and you'll notice that the bottom is going at a constant speed. Constant. But look at the top. Can you see that? Notice how as it gets closer to the bottom, it's definitely going faster as it gets closer to the bottom than it was near the top. See, it's falling slowly, slowly, slow, a little faster, a little faster, a little faster, and then it absolutely takes off. So if you thought, well, both parts of the ladder must be moving at the same speed, that's actually not a correct assumption. Different parts of the ladder can move at different speeds, even though it's one ladder. You can see it in the picture. The bottom is going constantly at 1 feet per second, right? Change in x over change in time, 1 feet per second. But the top of the ladder is definitely increasing as you get further down. So with that in mind, that means we got math to do. All right, I'm going to draw the picture. Here's the wall. Here's the ground. Here's the ladder. So what do I know? I know the ladder is 20 feet long, right? Let me try to get all of the information here. Well, we're going to assume that the wall is at a right angle with the ground. Otherwise, we can't do this problem. And we have some sort of course, x distance here. We have some sort of y distance there. We are told that the x distance is how fast is the top of the ladder falling when the ladder is 12 feet from the bottom of the wall. So we actually know that x is 12 at some point. That's a given. What else are we given? We're given that the mother is pulling from here, pulling that way. And so that would be the change in the x distance at a rate of 3 feet per second. So dx by dt is 3 feet per second. And I'm going to leave that positive. There might be people who would go, oh, wait a minute, you're going to the left. Shouldn't we call that negative? Well, you could if you wanted to. You'd get, get a negative answer. But I'll just assume there's only one direction that x could be going. You can't push the ladder through the wall. So that'll be my positive direction to the left here, okay? So hopefully that doesn't freak anybody out. So this is 12 feet. This is 3 feet per second. And again, I'll call it positive. My ladder, however, is, if this point's going that way, then this point's going this way. And that's actually what I'm looking for. I want to know how much y is changing, right? How fast is the top of the ladder falling when x is 12 feet? Now I need some sort of formula that relates x and y. Any ideas? A chill just went down your grade 8 teacher's spine. It's Pythagoras. Yeah, there you go. X squared plus y squared is equal to 20 squared. So there's the formula that's going to relate everything. I'm going to do a derivative of both sides. So this is going to be the derivative of x with respect to time. So I'm doing the derivative of both sides of the equation with respect to time. So this is going to be 2 times x times dx by dt. This is going to be 2 times y times dy by dt. Oops, t. And of course, no matter which variable I'm actually doing a derivative for, a derivative of a constant's nothing. So 400, the derivative of 400 is nothing. And from here, I'm going to plug in the numbers that I know here. Oh, I guess I have one other number I can find. If x is 12, I can actually solve for y. So y squared would equal, what's 400 minus 144? Is that 256? Oh, good, that works out nice. 16. There we go. So y is 16. So I know x, I know y, I know the rate of change for x, so I know this part of the formula. This is what I'm looking for. I like to simplify my formula before I plug in numbers. So dy by dt is 2x times dx by dt. I guess if I move that to the other side, I have to make it negative. And again, there's people going, oh, but I already had x as negative. That's fine. It doesn't really matter about the sign on this one. And then divided by 2y. The 2's cancel. That's nice. And so my answer will be, plug in the numbers. And away we go. Okay, so what did we know x was again? Let me make this a bit smaller so we can still see our numbers. X was 12. dx by dt was 3. And y was, what was y? 16, we just solved for it. There we go. Okay, I can simplify that a little bit. That's 3 and 4, so that's negative 9/4. So I'll go to a decimal on this one maybe. So negative 2.25. And you could do unit analysis if you want, but you'll end up in feet per second, right? Because you had feet here, canceling feet here, and this is feet per second. So those feet cancel and you're left with feet per second. That's another good way to make sure that you've got your formula working right. If you get the units that you think you're supposed to get in the final answer, that's another nice way to check to see if you're doing it right. Okay, I think those examples are enough for today. We're getting low on time anyhow. So I'll stop my video.